Okay, Chem 20s. What I wanted to do is I just wanted to review a little bit about strong acids and weak acids, strong bases and weak bases. And so please make sure that you have your data booklet out and make sure that your data booklet is open to your table of acids and bases. If you need to pause the video in order to get ready, that's totally fine. But I'm gonna dive right in here. So when we look at our table of acids and bases on page 8 and 9 in our data booklet, we see that we've got a column that gives us the names of all of the acids. We've got formulas for all of the common acids that we'll be using in Chem 20 and Chem 30. And then what we see beside the acid column is the base column. Now, anything in the base column can act as a base, but we'll talk about that here in a little bit. So when we take a look at our acid column, there are certain types of acids. There are strong and weak acids. Please recall that the top 6, those are our strong acids. So it's important for us to understand that those strong acids, they will react with water 100% or greater than 99%. And so those strong acids, they really give a lot of hydronium into our water. When we look below, okay, we've got hydronium, which is, the chemical that makes something acidic. And then below that, we've got all of our weak acids. So from here on down, those are our weak acids. And weak acids, when you add them to water, they often react less than 50%. Most of the time, only around 1% of those molecules will actually react with water to make hydronium. So it's important to recognize those are our strong acids. Anything below that is a weak acid, and they'll mostly stay together. They mostly will not ionize. It's kind of the opposite situation for bases, though. So the only strong base that you know of right now is way down at the bottom. It is hydroxide. Anything with hydroxide in it, that is the only strong base that you know of so far. Now, strong bases react to give 100% hydroxide. What that means is when they split up, if they split up, they will produce 100% hydroxide that actually split up. Anything else in the base column, is a weak base. So all of these things, these are all weak bases. It's important to be able to navigate the data booklet and be able to understand what's going on here. So when we look at these, phosphate is a weak base, carbonate is a weak base, ammonia is a weak base as well. They react similarly to weak acids in that they only give less than 50% of the hydroxide, or they will get often less than 1% of our hydroxide. They will react with water to give less than 1% of the hydroxide. So it's important for us to be able to use this table to understand it. Now, I will say this, is that anything in the base column that's way up here, you should completely ignore, right? A lot of these are our group 17 ions, iodine, bromine, chlorine, and nitrate in particular. So those are ions that will never really act as a base. They are given in the data booklet, but you'll talk about that in Chem 30. Okay, so what does this mean? Well, I've got on the smartboard here, I've got 2 beakers. And what I would like you to do is I would like you to, get a sheet of paper or something like that, and I want you to draw a couple beakers in here, just draw 2 cups or something like that. And what I want to do is I want to add some strong acid to water and some weak acid to water. And then I want to kind of prove to you what's going on, some of the properties of strong acids and weak acids. So we're going to take a very stereotypical strong acid. we're going to talk about hydrochloric acid. So our hydrochloric acid, that's going to be our strong acid. That's the one that we're going to think about as being a very typical strong acid. And then our weak acid, just because I'm lazy, what I'm going to do, my weak acid that I'm going to choose is going to be hydrofluoric acid, HF. The reason why that is because I don't really want to write a lot, and this is kind of the simplest weak acid that we know of. So I'm going to choose hydrofluoric acid, so one strong acid and one weak acid. And what I'm going to do is I'm going to add, we've got water in this beaker, we've got water in this beaker. I'm going to add maybe 3 or 4 HCl molecules to the water, and then I'm going to add 3 or 4 HF molecules to the water, and we're going to see what happens. We're going to see what properties we should be able to predict based on the fact that one is a strong acid and one is a weak acid. So a strong acid, think to yourself, a strong acid reacts with water 100%. So I'm going to add some HCl into the beaker, and the very first time I add an HCl, it immediately reacts with water. It reacts with water to create hydronium and chloride ions. So that's one. I added one molecule of HCl and immediately reacted to make hydronium and chloride. Okay, I'm going to do that a few more times. I'm going to add another one. As soon as I add another one, it immediately reacts with the water to make hydronium and chloride ions based on the modified Arrhenius reaction. I'm going to do it again. It immediately reacts to make hydronium and chloride, and then I'm going to do it a fourth time, H3O and Cl minus. One thing, hopefully you'll kind of recognize here, is that every time I add an HCl, I made a hydronium. 100% of it reacted with the water. Let's figure out what's going to happen with the HF, though. Our HF is a weak acid, so it reacts less than 50%. What I mean by less than 50% is that very few of them are going to react. So what we're going to do is we're going to add 4 HF molecules. Just like we did earlier, we added 1, 2, 3, 4 HCl's. I add an HF, and it's not going to react. Maybe the first one does, but just for the sake of this argument, I add 1 HF and it doesn't react. I add another one, the second one still doesn't react. I add a third one, okay, maybe the third one does react. It does make hydronium and fluoride minus, but then I add a fourth one and it doesn't react. So we take a look at these two beakers, one where the acid reacted 100% of the time, and one where the acid reacted less than 50% of the time. So just 1 out of 4. We take a look and we try and figure out, well, what properties could we predict from this? Well, there's kind of 2 diagnostic tests that you've learned about already this semester. One of them is a pH test, and one of them is a conductivity test. So what I want to figure out is what's going to happen to the pH of these solutions and what's going to happen to the conductivities of these solutions. Which one do you think is going to have a lower pH? Remember, lower pH means more acidic. More acidic means more hydronium. So we should predict that the HCl solution will have a lower pH. And we predict that the HF solution should have a higher pH. One is more acidic, one is less acidic. Okay, that's fair, and we'll double check that here in a second. What about conductivity? Do you remember what conductivity is based on? What determines the conductivity of a solution? I'll give you a hint. It's the number of ions present in the solution. Which one of these, the strong acid or the weak acid, has more ions present in the solution? Yeah, I totally agree with you. The strong acid, as long as we have equal concentrations of the original acid, right? We added 4 and we added 4. the strong acid should have more ions. Look at this, it's got 8 ions, whereas the weak acid only has 2 ions. And so not only is it going to have a lower pH, it's going to be more conductive. And I'm going to show you an example of that right away here. So we'll flip over to the example right now. Okay, so here we see 2 solutions. We've got solution number 1 here, and then we got solution number 2 here. One of them is a weak acid and one of them is a strong acid. And we're going to use 2 different diagnostic tests to be able to figure it out. Over here on the left, I've got some pH probes. And the pH probes are reading close enough to the same value in some distilled water that I think it's reasonable for us to use them. So one is reading 7.2 something and one is reading 7.1 something. And then we're going to test the conductivity, and we're testing the conductivity by bringing in a conductivity tester. Here we have our conductivity tester sitting in distilled water, and you can see the conductivity tester isn't turning on. That's because distilled water doesn't contain enough ions to be able to engage the light bulb, to turn it on. So what we're going to do is we're going to test the pH first. So we'll take the first pH probe and stick it into the one solution. And then we'll take the next pH probe and stick it into the other solution. So solution number 1, we can see solution number 1 has a pH of 3.70, 3.71, something like that. So we'll go ahead and write that down. 3.71. And I know it's kind of messing around, it's going up and down, but that's fine. That's a good initial measurement. And then for solution number 2, it looks like it's reading a pH of 0.85. So a pH of 0.85. Now I should tell you, these solutions, the original acid solution was at the exact same concentration, so immediately you should be able to tell which solution is the strong acid and which solution is the weak acid. Take a second to pause the video to figure out which solution was the strong acid and which solution is the weak acid. Okay, so hopefully you should know one of these is a strong acid and one of these is a weak acid, but we can also use conductivity to test as well. Remember, weak acids don't produce very many ions because they react less than 50%, often only about 1%. So when I take my conductivity tester and I put it into solution number 1, I don't know how easy it is to tell, but solution number 1, the light bulb is turning on, but it's not turning on very much. So it looks like solution number 1 is weakly conductive. When I put it into solution number 2, here we go. Yes, it's extremely conductive. The light bulb is turned on really, really bright. And so absolutely, our solution number 1 has low conductivity or conductivity. It's not no conductivity, but it's low conductivity. And solution number 2 has high conductivity. Using either one of these tools, we could have identified that solution 2 was the strong acid and solution number 1 was the weak acid. Okay, so we've talked about strong acids and weak acids, and we're also going to talk about strong bases and weak bases. Remember, strong bases, when we look at our data booklet, the only strong base is something that has hydroxide in it. Sodium hydroxide, potassium hydroxide, calcium hydroxide, whatever. So in this particular case, we're going to choose a really stereotypical one. We're going to choose sodium hydroxide. I don't need a modified Arrhenius equation to tell me how sodium hydroxide makes hydroxide. It just splits up and does make hydroxide. We're going to choose a weak base. Okay, so we're going to choose any weak base in here. How about we choose a cyanide ion? Sure, no problem. Let's choose a cyanide ion. So this is cyanide ion you can get from a solution from sodium cyanide or potassium cyanide, something like that. So I'm going to add, same thing, 4 sodium hydroxides to my water. Every single time it's going to split up. So it's going to make sodium ions and hydroxide ions. I don't need to react with water to prove how this gives hydroxide. I do it 4 times. Again, it's going to be really conductive, right? It's got tons of ions in it. Now we're going to do the same thing for cyanide. Now when cyanide, in order to make hydroxide, we need to react it with water. And the cyanide is going to steal a hydrogen, so it's going to make hydroxide plus HCN. But it's only going to do this as a weak base. It's going to do this less than 50% of the time. So I'm going to add 4 cyanide ions. 1, 2, 3, 4. And only one of them, right, less than 50% is going to react. So one of them turns into HCN and then OH minus. The CN reacted with the water and turned to OH minus and HCN. So we take a look, and with bases, it's a lot harder to use conductivity to test because if in weak base solutions, often they came from ionic compounds. So there's tons of ions. Conductivity is not a great thing to use to test between for like a weak base and a strong base. But something that is great is pH. Take a look at these solutions, and what's going to be the main difference between them? We've got lots of hydroxide and a small amount of hydroxide. So something that has lots of hydroxide is going to have a really high pH. That's why in your notes you wrote down that it has a pH around 13 or 14, something like that. And then this weak base is going to have a relatively lower pH. It's still going to be above 7. It's still basic, but this one's going to have a lower pH. So let's take a look at a couple solutions right now, and let's try and see if we can figure out which one is a strong base and which one is a weak base based on the pH of the solutions. Okay, we got 2 more solutions. We got solution number 3 and solution number 4. And these 2 solutions have the similar concentrations, but one of them is a strong base and one of them is a weak base. Again, we can't really use conductivity because there's lots of ions. There's often bases are attached to ionic compounds. But what we can do is we can use pH. Now we've got 2 pH probes. Again, they're reading fairly similar, 7.1 and 7.3. Okay, no problem. So what I'm going to do is I'm going to put the first pH probe into solution number 3. And then I'm going to put the second pH probe into solution number 4. And solution number 3 is reading approximately 13.48. 4950, and then solution number 4 is reading approximately 11.5. So they're both bases, but take a second to try and figure out which one of these solutions is the strong base and which one is the weak base. Okay, hopefully, pause the video or either you had enough time to figure it out, but yeah. The one that's the strong base is going to have the highest pH. So solution number 3 is going to be the strong base, and solution number 4 is going to be the weak base. Hopefully that gave you a little bit of an idea as to what's going on with strong and weak bases and strong and weak acids. Let us know if you have any questions. Come visit either myself, Mr. Walton, or you can see Mr. Zielinski, Mr. Zukowski, or Madame Belzile at Flex or Lunch, and also Mr. Reynolds as well. Thanks. Bye.